Okay, good morning. Welcome to
FamilyMath number 944.
Math 944. So this morning I had you read chapter 6 in Infinite Powers. Actually, can you turn on the light? What was this chapter about?
It was about the 3 fundamental problems of calculus.
Okay, and what were those fundamental problems?
So it was... So the first one, I'll make it out of order, but the first one was you have a curve. Right there. You have a curve and you need to calculate the derivative everywhere. I think they use instantaneous speed or slope.
Okay. Oh, sorry that the camera cord was in there. All right, so the first problem is you have a curve and you're trying to find the slope of that curve everywhere.
Or the derivative everywhere, yeah.
All right.
And then the next one was given the slope or derivative of a curve everywhere, find the original curve. So how do you go backward?
Okay.
And then the third one is given a curve, find the area under the curve.
All right, cool. All right, so let's and then I asked you to come up with 2 things in the chapter that you wanted to talk about. What were those?
There was the Usain Bolt problem, or not really a problem, but
okay.
And then how they did instantaneous speed. All
right, cool. All right, so let's talk about these 3 problems, and then we'll do those 2 things. And hopefully that's not going to take all that long. All right, so if I have a curve. One of the problems in calculus is finding the slope of the tangent on that curve. That was the first thing?
Yeah.
All right. What is this? Just describe to me an approach how you might be able to solve this problem or think about it, or even why this is an interesting or important problem.
Well, what you want to do is you want to just zoom in on the point.
Okay.
So
you can zoom here if you want. Oops, sorry.
Instead of looking like a curve, you're going to get something that looks rather flat.
All right.
And then your tangent line, it just looks like an extension of that line.
Okay.
And then you get your tangent line. And the tangent line is useful for describing locally what a curve might look like later. Like, say you just have the curve up to there, and you don't know what it's going to do next.
Okay.
So the tangent line can give you, I guess, a first approximation at what it's going to do next, and then with better and better approximations and higher functions, you can get a better approximation.
Oh, good. Yeah, and so, for example, if we know that the square root of 100 is 10, we can use that plus the tangent line there to, the square root of 101 is approximately 10 plus, I think, 1/20, probably. All right, cool. All right, what about the problem? This is kind of an interesting problem. You know the tangent line everywhere. That was the second one?
Yeah.
Okay, so here, actually, your graph, let's say it looked like this. But this graph isn't the actual curve, but rather the slope of the tangent line. So if this is the point 2, I don't know what you want to pretend this is, 3? Even though that's not really scaled right. So this would be saying our curve at the point x equals 2 has a slope of 3. And here we want to be able to reconstruct the curve. Okay, so why could this be an important or interesting problem?
Well, if you need to go backward, like say like the velocity of something, but you want to know the position.
Okay. Yeah. Yeah, well that's interesting because he says the third one is finding the area under a curve.
The 2 and 3 are kind of similar.
Alright, so here I have a curve that maybe looks like this, and I'm trying to find this area. Alright? Why might this be an important problem?
That's the same reason as the second one. If you need to go backward in orders, like if you need to find velocity as opposed to acceleration, or position as opposed to velocity.
Okay. And yet it's kind of surprising these are connected. Do you remember from your calculus class the connection between these 2 problems? If you know the tangent line everywhere, you can reconstruct the curve and then finding the area under the curve.
It's the It's the relationship between derivatives and integrals.
Yeah, that's right. Do you remember what that relationship is called?
I don't remember what it was called, but the derivative of the inverse is the derivative of the integral is the original function.
Yeah, it's called the fundamental theorem of calculus. Cool. All right. Let's talk about the two things you wanted to talk about.
All right.